In this third micro lecture, I wanted to deal with the concept of how is water lost in the respiration and how or what mechanisms can be engaged to prevent from losing too much water, with also some examples of animals that may use these mechanisms. Again, repeating on what I have said several times already, that evaporative water loss is the main mechanism to lose heat. How can we get rid of heat? Simply by depositing water in some surfaces of the body, that when this water evaporates, it draws with it a certain amount of energy, which is not little. Of course, the problem is that you lose water. The heat of vaporization of water is 580 kilocalories, or 2.5 or 2,500 kilojoules per kilogram of water. Sweating is one of the strategies used by humans, horses, cattle, even camels sweat. The problem with camel sweating can be that although camels can sweat, basically the sweat is not seen, and that's because basically in the environment they live, the water disappears so quickly. But they do have sweat glands. The alternative is panting. Panting is a strategy used by animals that do not have or have very few sweat glands. And that is, for example, the case of dogs, sheep, goats, small gazelles, carnivores like felids or cats, for example, and even birds. Birds actually use a mechanism of panting that has also been described as gular flutter, but it's essentially the same mechanism. Sweating and panting, non-exclusive strategies. That means that an animal that can sweat can also pant. I mean, there's no exclusive, but there is a certain preference, and unfortunately we have no understand, or we don't have a knowledge why some animals pant, why some animals sweat. The fact is that both possibilities are there. Some animals prefer sweating, some animals prefer panting, some animals combine them. Issues with sweating: loss of salts. Loss of salts, which can be another disadvantage to it. This is data also from Smith-Nielsen, actually on panting dogs. And what this data shows is basically air going in or out through the nose, air going in or out through the mouth. And what Smith-Nielsen was able to demonstrate is basically that the panting mechanism is a mechanism in which dogs breathe in through the nose, but then most of the air, instead of leaving through the nose, they leave through the mouth. So inspiration through the nose, expiration through the mouth. That's not exclusive means of panting. He also demonstrated that panting can occur through the mouth only, in and out of the mouth. He actually has some data on that as well. Panting facilitates evaporation by providing convective flow. So this is one particularity of panting that sweating does not show, is that basically in panting you are moving air in and out at the same time. That convective flow facilitates getting rid of the water, eliminating the water and eliminating the heat. Unfortunately, as a disadvantage, panting can lead to alkalosis. And that's nothing new to you now. Remember the climber at altitude hyperventilating, becoming alkalotic? It's the same thing here. If the exchange of gases, the exchange through the respiratory system actually reaches the alveoli, so that basically CO2 is more eliminated, you then, so that there is more CO2 eliminated, you incur in this alkalosis. What Smith-Nielsen was able to demonstrate is that panting costs very little energy. Panting is actually a movement at very high frequencies, at what he calls the resonating frequencies of the respiratory system. And when you have a resonating system, basically it's a system that will require relatively little muscle energy in this case. we'll see how actually several animals deal with respiratory water losses. And here you have the first example of the kangaroo rat, and actually it was Knut Smith-Nielsen as well that provided a water and heat budget for this animal. And the gains of water for the kangaroo rat are mostly seen in the form of metabolic water. Remember, metabolic water is the water produced in metabolism. When glucose is oxidized using oxygen, CO2 and water are produced. This is the metabolic water we're talking about. Basically, the source of water for the kangaroo rat is 90% from this metabolic water. Free water in the dry food, even if their food is mostly seeds, it's also dry food, there is up to 10%, because these animals, kangaroo rats, do not drink. From this budget, these gains of 100%, how much is it lost? In the feces, very concentrated, 5%. In the form of urine, 25%. In the last lecture today, we will see how basically they can concentrate the urine and avoid losing too much water. 70% of the water lost by the kangaroo rat is actually lost through respiration, evaporation, and also a little bit of perspiration. The conclusion is that water is unavoidably lost in ventilation, although these losses can be regulated, and we will see that in a second. How can the water be regulated in the kangaroo rat? These arrows in blue and red give us a little bit of information about how much water can be recovered through the respiration at two different ambient temperatures. One example at 15 degrees or at 13, 14 degrees, the other example at closer to 30 degrees. And in here what you see essentially is that the amount of water per liter of air in the exhaled air when the relative humidity is at 100%, or in the inhaled air when the relative humidity is 25%. So what this essentially means is that the air that is inhaled is a bit dry, contains only 25% of relative humidity, the content of water is lower. When this same air is exhaled, at 100%, there is much more water that is lost. This is the difference between the two, and this is basically the avenues for loss. But notice that if we do the measurements, or if we do the consideration at 30 degrees, the inhaled air, which is relatively little saturated, has a relatively little water, when it reaches the lungs at this point, lung air saturated at 38 degrees, constant temperature, saturation, the amount of water that the own body adds to the incoming air is this blue arrow. This is the water that has to be added to make this new gas that's coming into the lungs fully moist at the full saturation of the lungs at 32 to 38 degrees centigrade. When this air is exhaled through this curve, when the air is exhaled, what happens here? There is the potential for recovering 54% of the water. The rest is going to be lost. This is the amount of water that is lost in the respiration. And this is unavoidable. You cannot do anything with this. We'll see that you can try to do something, but this is a certain amount of water that's going to be lost in the respiration. If this is happening at a lower temperature, the potential for recovering is much higher, up to 83%. We'll see in a second what is the actual mechanism for recovery. But the basis here is that respiratory water loss is unavoidable because the animal is respiring, and because it needs to be, the air that is inhaled needs to be saturated with water at the level of the lungs, and then the potential is what's going to be lost or recovered on expiration. This is the mechanism by which this happens. This is the mechanism actually consists of the nasal mucosa functioning as a storage of heat and humidity. And what you see here is essentially that during inspiration, the cold air comes in contact with the nasal passages and eventually will make it down to the lung. This is cold air cooling down this mucosa. The air is coming in. On expiration, this air that is now warm is coming out here through the same way. The concept that is important to see here is one of storage of heat and storage of humidity. The idea is that these nasal passages can actually store the low temperature or the cold that is coming with this air, because of course notice that what's going to be happening here, what's going to be happening is that this air is going to be warmed up and humidified. If in the way up or out this air leaves with the humidity from here and with the temperature from here, what do? We lose heat and we lose water. But if we take advantage that this has become drier and colder, in the way up, we can now exchange with the drier and colder surface here, warm it up and humidify it from the exhaled air. That meaning that the air that we exhale is colder and it's less humid. So this is the mechanism in which actually we use, or these nasal passages can be used for storing the cold and the water, or the cold and the dehydration that's happening here in terms of being recovered in the way out. This mechanism is actually seen in many organisms. This mechanism is the mechanism that works in the kangaroo rat. I'll show you that this mechanism is also partly seen in reindeer. In the reindeer, what has been measured is basically what is the exhaled air temperature at different ambient temperatures. So in this animal, actually from 30 to -5 degrees, the body temperature is constant. The reindeer can deal well within this temperature range. Body temperature is constant. What happens with the temperature of the exhaled air? The temperature of the exhaled air follows this line. What does this mean? This means that actually the exhaled air comes, or the temperature of this air that's exhaled is higher than the temperature of the inhaled air. It's higher than the temperature of the inhaled air. But it's still not the same temperature than the inhaled air. How does that work? Exhaled air temperature, yeah. Exhaled air temperature. No, of course. This is the exhaled air temperature in this graph, the ambient temperature in this graph. If these two temperatures are identical, they are equal, you would be following this graph, this line. But you are not following this line. The actual exhaled air temperature is above this line here. That means that, for example, take this as an example. At an ambient air temperature of 10 degrees, the exhaled air temperature is 23 degrees. Do you see that? That means that this animal is not able to exhale at the same temperature that inhaled, but at the same time it's not exhaling at 38 degrees either. It's exhaling at a different temperature, which is not 38 degrees. That means that the reindeer is able to extract in the exhaled air a little bit of the heat that would be lost otherwise, and a little bit of the water that would be lost otherwise. A similar mechanism than this has been shown in camels, and I'm going to show you the data. What is the basis for this mechanism? The basis for this mechanism is the existence of the turbinate bones. The turbinate bones are the bones that conform the nasal passages. And of course, what you may imagine here is that is the surface area in contact with the turbinate bones that matters here. In the reindeer, if you did a cross-section of these turbinate bones, you would notice these coilings here. What are these coilings for? Increasing the surface area over which the air has to pass. By increasing this surface area, it means that the heat and the water can be trapped in here, so for exchange. How would this look like in an animal that cannot do this? In a cow, for example. This is how it looks like in a cow. Notice that in the cow there is not increased surface area. So in this case, the possibility for storing part of this cold and dry conditions that are coming in with inhaled air, it's not possible here. In the cow, there's not going to be this potential, this possibility for actually holding the cold so that then the exhaled air is going to exchange with it again. But that is present in the reindeer. This exchanger system is instrumental in the conservation of heat and water. This exchanger, the efficiency of this exchanger is temperature depending. It can recover up to 75% of the heat, and it can recover up to 80% of the water that would be lost otherwise. So this is a rather important saving mechanism. In the camels, Knut Schmidt-Nielsen demonstrated a similar mechanism. Notice that he showed it in a different way, but basically what Schmidt-Nielsen was able to demonstrate, this is data from one camel, is that the respiratory water loss, the amount of water lost with the respiration, increases with body temperature. The higher the body temperature, the more the respiratory loss. And it also increases with respiratory frequency. What he was able to show is that respiratory water loss in the camels is actually increased during the day at the time where there is maximal heat load, but it's minimized at nights. And what he's showing with the data, this is actually oxygen consumption, and this is respiration. So what he noticed is that when oxygen consumption increased to a maximal, respiration was also maximized. This is the body temperature versus the water loss per liter of oxygen. And that increases during the day, but it's maintained low during the night. So what Schmidt-Nielsen was able to demonstrate with this data is that in camels, during the day, as we have said earlier, accumulation of body heat. Nevertheless, the camels lose water through the respiration. They cannot avoid it. They lose water through the respiration. However, during the night, those losses are much lower. And that's what basically this is shown here as well. And this data is actually looking at the relative humidity of the exhaled air. This is actually in a normally hydrated camel. During the day at 37.5 degrees. That's the ambient temperature. Notice what happens is that this is inspiration, expiration, etc. Every time this animal exhales, relative humidity of the air increases. What this means is that during the day, the camel is not able to exhale dehydrated air. When it's breathing out, it's losing water. During the night, however, the relative humidity during exhalation does not reach 100%. This is a saving of water that the animal is doing during the night. This animal was also severely dehydrated. So what Schmidt-Nielsen was able to demonstrate is not only that the body temperature of the camels accumulates or changes cyclically during the day, but also that these animals, particularly at night, are able to save water in the respiration by using this mechanism that we were describing in the reindeer. Questions?